It's not published yet. I'm self-confident enough to say we are the first who made it. I mean, the field of metal organic frameworks really pushed this topic. Make something that no one else can make.
Welcome to the 18th episode of Apple Finch Pudding, your gateway into the world of science. Today's scientist is Andreas Schneemann, a postdoctoral researcher in inorganic chemistry at the Technical University of Dresden. Andreas' groundbreaking work focuses on the development and fundamental understanding of covalent organic framework-based 2D materials. That's quite a mouthful and something we have to talk more about, but this research has resulted in multiple high-impact papers for Andreas. So welcome, Andreas, and thank you for being here.
Thank you for the kind invitation, Jeroen.
My first question is always the same. Do you have some kind of fun fact or a science joke or something for our listeners?
Many research efforts are related to energy conversion, energy storage. The fact is that the internet will consume in 2030 more energy than the whole of humanity did in 2011. So I think this is something to really think about, because we are moving a lot of stuff online, but servers, connections, they all cost energy. So we really need to think about energy storage, energy production, and energy conversion.
Wow, that's insane. So in 2030, only the internet will use more energy than the whole humanity in 2011.
Yep. This, at least I read that.
Yeah, I heard that's also something like because we're streaming a lot, and that actually takes a lot of energy because those servers need to run, and purely based on energy consumption, it's actually beneficial to have something downloaded compared to streaming.
Yeah, particularly if you use it multiple times.
Yeah, like if you're watching or listening the same thing over and over again on YouTube or something.
Yeah, so people should download the podcast and record it on a cassette or burn it on a CD.
As long as they listen, it's fine.
Yeah.
Okay, we'll start with the basics. So you work in inorganic chemistry. What is inorganic chemistry and how would you compare that to organic chemistry?
Inorganic chemistry is the chemistry of all the elements from the periodic table. You're trying to build new compounds, materials by connecting atoms. In the organic chemistry, you focus mostly on the elements that you have in nature, like the carbon, the hydrogen, the nitrogen, the oxygen, the sulfur, phosphorus, like only a few elements that can form large complicated structures. And we are looking at the rest of the periodic table. But I'm in the Department of Inorganic Chemistry, but in inorganic chemistry, you also need to look a lot into ligands and molecules that can coordinate to your inorganic compounds. So we also do quite a bit of organic synthesis, organic chemistry to connect linkers or ligands to inorganic elements. So I'm stuck in the middle, but more towards the inorganic side, I would say.
So organic chemistry focuses on the carbon and hydrogen and everything that we see in living organisms. Inorganic components, so all the other elements of the table of elements. But you're actually working in between, so you use both a bit.
Yeah, I mean, you introduced my research topic. I work on covalent-organic frameworks. So this already has the word organic in it. So we're building larger structures that contain inorganic moieties which are connected through organic moieties. And also a short correction, I'm not a postdoctoral researcher. Actually, I have my own small research group. So I'm a junior research group leader. So I have currently 2 PhD students that work in my lab and 1 master student. And I also take care of some of the students of my mentor.
Okay, so you have your own lab. So
I have. I'm not a professor yet. So in Germany, the system is a bit different than compared to like the US or to many other countries. So you do your postdoc, and then you go to a university, then you do something called a habilitation. I don't know if you have that in Belgium. I'm actually writing another book, another thesis, based on the results of my students and my own work that I do in the lab. And I have to hand it in, I have to defend it. You do that after roughly 5-6 years. And then I can become a professor at that point.
So it's actually like an additional degree after your PhD.
Kind of like that. So it's, I mean, there are many concurring systems right now in Germany. So there's also junior professors. Those are then directly after your postdoc, you become a junior professor. And there's also now tenure tracks, but the more classical way, which I'm pursuing, is the habilitation. And yeah, I think if you compare it, it's like an assistant professor in the international system. So I mean, I have my own little lab, my small group. I work on my own projects. I help out in teaching.
You need to get to find your own funding as well.
Yeah, exactly. So I'm currently self-funded. So I have 2 projects. In Germany, there's a very good funding landscape, and also for young scientists. So I was very lucky to obtain some funding, and now we are working on the projects that I got funded for. Yeah.
Now we're going to dive a little into your topic, and also again starting with the basics. You're talking about covalent organic frameworks. What are those? What are covalent organic frameworks?
So essentially, I mean, you can imagine what a framework is. A framework is a regular periodic crystalline structure. So where you have repeating units that expand through 3D space. And in a covalent organic framework, you have linker molecules, which are highly symmetric, like triangular shaped or square shaped, and they are connected through a second linker. And then you build up a structure, porous, regular structure.
So they are covalent. How does that differ from other connections, like have ionic or hydrogen bonds?
The covalent organic frameworks community is very closely related to the metal organic framework community. So this is a research topic that started in the early to mid 90s and is now a really big research field. I used to work in this field during my PhD studies. So there you have highly symmetric metal clusters or metal ions, which are then connected through linear or tritopic, tetratopic linkers to build up also a porous structure. And in covalent organic frameworks, you remove the coordination bond that you have in the metal organic framework and replace it by a covalent bond. Do you have some background in chemistry? So you're a plant physiologist, if I...
Yeah, that's true. I have some basic, but let's try to explain it as simple as possible so most people can follow. So like maybe just a covalent bond. How would you explain that?
Yeah, a covalent bond is a bond where both partners have similar electronegativities. In an ionic bond, you have very different electronegativities. So electrons are essentially shared between the 2 partners of the bond, so that if you go back to the first semester chemistry, you are filling your octet with the electrons of the partner, and then you have a quite strong bond.
So an electronegativity is like more or less how strong the atom is pulling at the electrons.
Yeah,
and
exactly.
In this case, both are pulling equally, so they are sharing the electron.
Yeah, exactly. These covalent bonds are mostly found in the first period in the periodic table. The boron, carbon, nitrogen, oxygen. Maybe the most famous bond in this regard is the imine bond. So this is a bond that many people use.
What bond? Sorry.
Imine. Imine.
Okay. I don't know it.
So if you have an aldehyde, you know what an aldehyde is?
Yeah, sorry. Yeah.
So you have an aldehyde, which is reacting with an amino group. So the NH2, you do a condensation reaction, and then you are linking the nitrogen from the amine via a double bond to the carbon atom that was connected to the oxygen of the aldehyde, and you form water. and have a condensation reaction, and then you have this imine bridge. So this can be used to link organic molecules together into a framework.
Yeah. So we're talking about organic chemistry right now.
Yes.
Yeah. And so you have these covalent bonds, and those produce structures, you said, that also are repeating structures. Is it like, so that's a polymer?
Some people call it a polymer. It is kind of a polymer. So there's a huge, how to say, controversially led discussions, because essentially it's a polymer in 2D. So some people call also covalent organic frameworks 2D polymers. It's a kind of an interlinked fields. There are different schools of thoughts. So in a 2D polymer, there are some definitions that say you have the crystallization of the components first, and then you form the bonds between them. So you're arranging your components, then you form the bonds. In a covalent organic framework, you are doing the polymerization and the crystallization in one step. So the interesting thing that many people look at is when you build these structures, you're creating some voids between the molecules because you're building a network of larger molecules, and in between the molecules, you have some free space. And people want to use this pore space to do actual chemistry in it.
Okay, so it's like, to put it roughly, like some kind of fishing net that you're creating. So it's a porous structure. And what can we use it for? Why are you making those structures?
So there are different, also different ideas. So, I mean, you do these syntheses usually in wet chemically. So you put your starting materials into an ampule. You get your burner, your hydrogen oxygen burner, get a super hot flame, seal the ampule, put it in the oven for a couple of days, and then you get your structure. You still have the solvent inside the pores, and then you try to remove it by different means. And basically then you have nothing, so to say, in the pores, or then of course air or whatever gas you expose it to. And this can be very interesting, for example, for gas storage. That in the beginning of the research field, gas storage, hydrogen storage, because you have an extremely light material, it only consists of light elements, and then you can fill the pores with any kind of gas molecule. For example, in the beginning, hydrogen storage, very big topic. Like as a energy carrier, hydrogen is very interesting for the future because it's light, it has a very high energy density, and in porous structures you can store a lot of hydrogen compared to just having it in a gas tank without applying too much pressure. So this was in the beginning a big research area, but it kind of faded away. Nowadays, I would say energy storage is one of the biggest applications here, because if you imagine your framework, your Fisher net, so to say, and you have certain functional group that can interact with ions, then you can use them as ion hosts in batteries or supercapacitors for energy storage. This is something we are looking into. You can use it for filtrations, like if you have your net structure, one molecule goes through easier, the other not as easy, then you can make a membrane out of it, for example, and get some purified gases from it.
When you say we use it to catch or to store gases, do you imagine it like the fishing net is a balloon that is being filled, or are the gas elements sticking to the surface?
Yeah, this is it's classical adsorption. So you are sticking the gas molecules to the inner surface of the material. So you can
it's
get
a sticky net.
It's kind of a sticky. always depends, of course, on the functional groups that are on your linker molecules. How can they interact with gas molecules? Do they have some preferential interactions with certain gases? Can you differentiate between certain gases? And yeah, I mean, the field of metal organic frameworks really pushed this topic. Like previously, the covalent organic frameworks, they have been investigated now since roughly 2005. That's at least when the term was coined. So it's a relatively new research field.
I can also imagine that you have a lot of different chemicals, like you also said that you can include in those nets. How does that affect the structure and its functionality? Like what chemicals do you use in your research?
So now we come again to the point. You introduced me as an inorganic chemist. So we try to make the links between the organic structures, inorganic moieties.
So you're connecting inorganic and organic structures. That's what you're saying.
Yes, exactly, covalently. So if you remember, I explained the metal organic frameworks. There you have the coordinative bond. So it's a more polar bond compared to the covalent bond, where you have the metals inside the bridges between the organic parts. And in our case, we want to have covalent inorganic moieties, which are then bridged through the organic moieties.
So we'll forget I introduced you as an inorganic chemist. You're just a chemist. I introduced you as a chemist right now. Okay, so you're using both those structures and you're connecting them. In my head, that's a bit unusual because that's maybe because of how I studied it or whatever, but I always see like you have inorganic chemist and organic chemist, and now you're actually linking those two structures. Is that something that you find in nature as well, or is it purely man-made?
If we look back at the origins, I think the terms were coined, the organic and the inorganic chemistry, like a couple of 300 years ago, when it was thought that inorganic materials cannot be made by living organisms and the other way around, that they are strictly separated from each other. But I think you find some hybrid structures definitely in nature.
So I'm a few hundred years backdated in my head, but that's
no. So you have to consider the coordination chemistry is a really big field where you have organic molecules coordinating to metals. Simple examples would be like acetate as the anion of the acetic acid, which can coordinate, let's say, to simple metals, or maybe an even better example would be kidney stones. I think those consist of oxalic acid and calcium, and you form them in your body. I hope I'm not talking nonsense, but there are quite some examples where you have like simple organic molecules forming coordination bonds in nature to inorganic moieties.
And you say like maybe that's less relevant now, but it has been used to look at the storage of hydrogen for energy usage. Now that's not being done anymore, or is it still ongoing?
So I'm pretty sure it's still ongoing. It's very difficult to store hydrogen. I mean, it's the smallest.
It's quite explosive.
Smallest atom. Well, it's not explosive if there's no oxygen around. So you need also. Yeah,
you got me there.
And if there's no flame, of course. I mean, hydrogen still burns, but needs something to burn with. So the most promising approaches. So there are also like in my postdoc, I worked on hydrogen storage. Are currently carbon-lined tanks where you put high pressures of hydrogen. I mean, it's the same issue with with the electric vehicles. How often you have someone tell you, I'm not getting an electric vehicle. What if I need to drive 600 kilometers? I have to charge in the middle. That's annoying me.
I've heard that a few times.
Yeah. And with hydrogen, it's the same issue. If you want to go to private transport sector, you need to store a lot of hydrogen. So you need 4 kilogram of hydrogen in order to drive roughly I think 400 kilometers. And 4 kilograms of hydrogen is quite a lot by volume. So it's roughly a 400-liter tank, I think, you would need if it's not compressed. I have to look up the correct number. But the volume is gigantic, so you need to compress it. And if you have porous structures, the gases will come out of the gas phase. Like 1 mole of an ideal gas has an expansion of 22.4 liters at 0 degree Celsius. And if you can store that in a solid phase by absorbing it, you will reduce that volume drastically, right? So you need just 1 mole of a material that can take up hydrogen, like magnesium, for example, can do that very well. It will form a magnesium hydride. And then you have a much smaller volume. You can store your 1 mole of hydrogen. But the problem is that this material, for example, is too stable. So you can get it connected, but you cannot release the hydrogen without going to roughly 300 degrees centigrade. This is
that's kind of a big problem. So you have your hydrogen, you take it with you, but you cannot use it because it's stored in the material.
Yeah,
okay.
And that's why the porous materials, they have much smaller hydrogen binding energy. So it's just physisorb. There's no chemical bond. It's just surface interactions. Mm-hmm. And there you have the issue that it's, for practical applications, stored bound too weakly. So you need to find too weakly. So you have a problem called hydrogen boil off. So if you park your car, you filled it with your hydrogen at the future hydrogen station, your hydrogen will just desorb from the surface and you will lose it overnight.
Okay. Yeah. So it will just get released when you're not driving as well.
Yeah. Exactly. Yeah. So you need some special pressure tanks for that. Those are being developed, and there are projects in the US. There was, for example, in the San Francisco Bay Area, there was a hydrogen ferry where hydrogen was stored in pressure tanks. So there are some pilot projects where people are trying to use hydrogen as a energy carrier for vehicular transportation. But for the private sector, it's still an issue to store it in a way that the tank doesn't get too heavy, that you have enough to drive 300-400 kilometers without having to worry where to fuel. And of course, in Europe, we don't have an infrastructure for private cars. Mm-hmm. You also have to consider you need to fuel in a reasonable time. People are used to fill their car in like 2-3 minutes.
That's one of the big problems with electric cars as well, right?
Exactly. This is why it's the same people who are complaining about the limited reach. They will also tell you that I don't want to wait for an hour or 30 minutes to quick charge my car to like 80% again. So this is something you have to deal with when considering this. And I mean, also when you design materials for storing these energy carriers.
Based on your knowledge and your feelings about, and not actually feelings, but on what you know about the topic, do you think like hydrogen is one of the energy carriers for the future, or do you think we will need to use something else?
I think hydrogen will be a energy carrier of the future. I mean, if we find a way to produce it cheaply, to produce it where it's needed, because I mean, you need a lot of energy when you produce the hydrogen, so you need to produce it somewhere where you have a energy source, like, I don't know how to say,
maybe
water
in
power.
A desert, or with a lot of solar panels.
For example, or at a water water reservoir, like where you can use like water turbines. For example. Yeah. And then, of course, you need to store the energy there, transport it somewhere. So that's maybe like also an issue if you consider getting like a hydrogen grid. But I think it's a development that's just starting. I mean, if you think back, how long did it take that electric cars are now so popular, right?
Yeah, that's true.
And you always have to keep the consumer in mind. Everybody switched now to electric cars. Made an investment, and then we are building up a grid. I think Germany is still a bit behind, but other European countries are doing much better. The US is also doing much better. I think we will go with electric cars, and the hydrogen probably will be something that will start appearing later if we get the technology to be cheap enough and to be market ready, I think. Yeah.
So maybe electric cars will be the first step.
Yeah, I mean, it's a very transformative time now, I think.
Mhm,
Like if I would get a new car, I probably would also consider going
mhm.
electric. I mean, there's also the support from the European Union, I think. When you buy a car in Germany, the fueling station will be covered to some extent by the government. It's just a problem if you have to rely on street parking and don't have your own parking spot, so to say, where you can connect it. Yeah.
While we're delving into the electric cars, can your research also be used in storing electric energy
Um,
or just the field? Is there
So
some?
yeah, of course, the field is there are a lot of discoveries in terms of different battery systems, different ion storage systems. So there's like classical lithium-ion batteries, lithium-sulfur batteries, sodium-ion batteries. So you have always to consider lithium is a very finite source on Earth. I think it's like 5 or 6% ppm, sorry, not percent ppm of the Earth's crust, and sodium is much more abundant, for example. So commercial sodium-ion batteries can make a big change, I think.
Yeah, I also heard that like the batteries right now are the most expensive part of your
Hmm.
electric car. So
Yeah.
if we can improve that, make that cheaper and make it last longer, that will
Mhm.
be a huge boost for the industry.
Yeah, I think so. I mean, Tesla is also right now investing in Germany hugely. So last year they just opened a battery factory close to Berlin. Energy storage and batteries generally in chemistry is a very big topic.
Is that something you would like to collaborate in those in that field of creating actually new batteries?
So I'm not an electrochemist, but I like to think about structures that can help there. So using the frameworks that I'm building also as cathode or anode materials in batteries. But I need to rely there on collaboration partners, of course. So I can just think about structures that we can make or that are interesting to explore, prepare them in the lab synthetically with my students, and then reach out to the people that are actually good at it. So my mentor is doing quite a lot of work in battery research, and we have a good collaboration going on there.
And so you're working on those covalent organic frameworks. Do you have some outputs or some interesting findings that are based on your work?
So we have now had our first publication of my own lab. So I'm very
Ah,
happy about that.
congratulations.
So what we are looking into, so part of my lab is funded through a so-called collaborative research cluster. So in Germany, the German Research Foundation, they have different programs, and the collaborative research cluster is like a local funding program. So you are trying to collaborate with like 20, 25 groups in one university to work on a bigger topic. So the topic that we are working on is synthetic 2D materials. So the research cluster is called Chemistry of Synthetic 2D Materials. And the framework structures that I just described, they are linked only in 2D, they are layered, and we are trying to exfoliate them into nanosheets. And this now, we published our first paper on this, and we can tune the thickness of the sheets that we are creating by the functional groups on the backbone of the frameworks. So this is really
So you're
exciting.
yeah,
Yeah.
so you're creating those sheets and you can actually adjust the thickness based on the chemicals that you're using.
Based on the functional groups that are connected to the sheets. So the sheets
Okay.
they are layered when you prepare them, and
Hmm.
through ultrasonication we can exfoliate them into stacks of roughly 1.5 to 2 nanometers. So that's like
Oh,
4 to 5 layers roughly. Yeah. So
okay.
this is quite a nice. Of course, it would be cool to have only one layer. One
Yeah.
molecular layer would be like the end goal. But yeah, this is like something we worked on and successfully did. And then in my other topic, we are working on new inorganic linkages between the organic moieties in covalent organic frameworks, and we made the first boron sulfur-linked covalent organic framework. It's not published yet. Maybe someone else made it and also didn't publish yet, but I'm self-confident enough to say we are the first who made it. And it's a very fundamental research, So I like to do fundamental things because if you get closer to application, there's a lot of people. And I'm a very small guy. I have a small team. So if I want to compete with the biggest groups in the world, it's super easy to get scooped. If you have a good idea, chances are someone else is also having it, because most of the other scientists are not stupid. They're usually very smart, highly creative people. And if there's an application involved, there will be funding. And I have to be a bit careful there. Also in Germany, the research funding is very nice, that you can also work on fundamental ideas to understand structures, to discover new materials that may not have an immediate use, but that may be interesting in a couple of years. So I can work in this little area and discover something and maybe useful, maybe something interesting for someone to pick up later, and to work it into a useful application. But yeah, I like to do just chemistry in the lab and discover something new and make something that no one else can make. Whether it's useful or not is a different question, but we are gaining knowledge, so it's worth pursuing it. So that's the goal of science, is creating knowledge, right? So
that's true. Yeah, because you were talking, you have to create it like 5 molecule layers together, and you want to get it into 1 molecule layer if possible.
Yeah.
But why? Is it just because it's fun and because it's interesting and you learn new stuff, or does it have a goal? Does it have an application?
If you consider 2D materials, I think the most famous 2D material is graphene. So it's a single layer.
That's like a pencil, right? The carbon in a pencil? It's graphite. That's 3D.
It's graphite, yeah. So graphite is a 2D layered structure consisting of the graphene layers. So
okay.
And I mean, there were some very interesting findings, because you completely change the band structure, so the distance between the conduction and valence band. And for physicists, those are really interesting, because you get superconductors. So materials have at the nanoscale, they have completely different properties than in the bulk scale. So if you make a single layer of graphene, so exfoliate your graphite, you get completely different properties. And in our case, like if we go back to energy storage or to gas separations, if you have a membrane that can distinguish between 2 molecules, for example, and it's ideally a single atomic layer thick, the diffusion barriers will be much lower, so you can do your separations more efficient. If you cast it into like a membrane with a support, you have a much better distribution of the layers. Like imagine you have one big stack, you try to put it into a support, it will be only in one spot. If you like a deck of cards, you are increasing your outer surface area, and you can distribute the sheets much better into a membrane with a second material, for example, with a support material, or on top of some holy material. Like you have a material, a support that has holes, but it's not so easy to make nanometer-sized holes into a large wafer. But if you have 100 nanometer, 50 nanometer pores in a large bulk material, you can cover them with your sheets, and then you separate your 2 molecules through the sheets that are on top of the support.
Yeah, so you're actually creating membranes to separate one molecule from another.
Yeah, this is what we are trying now. So this is now the follow-up work to like the finding. We can make these layers super thin. Now we are trying to distribute it on surfaces. We were able to show already that for ion diffusion, we can alter some membranes and have a higher diffusion of ions compared to the bulk framework when we put it in. It's also for energy storage applications. If you have much thinner materials, the ions can diffuse much quicker to the storage sites. So this can, for example, have an effect on the charging speed. The redox reaction that happens in your battery is then the rate determining step, and not the diffusion the ions through the bulk of the structure. Like if you imagine you have like a structure, a huge structure, and the ion needs to diffuse all through it to go somewhere in the middle of it, or if you have a lot of tiny sheets and the ions can just readily go to the reaction sites, to the redox reaction, get stored.
So, and redox, that's reduction and oxidation reaction. Yep. So there's an electron being transferred. And so you're actually saying that the redox reaction can go as fast as it can, because if you have that really thin layer, the chemicals are actually transported as fast as possible, or the electrons.
Yeah, you have to think in this way that if ions go somewhere, they have to pass through, they have to diffuse through the bulk of the structure. There's interparticle diffusion. There's a lot more processes that are happening, and if you just like get the materials as thin as possible, you have quicker ion storage. Yeah.
And also you said, so these membranes are used to separate materials. A while back, we had an episode on desalination of seawater. So we put seawater at one side and a membrane. And when there's a pressure applied, the water gets pushed through, but the ions don't get through. Is that something that you're looking at?
So is it called water osmosis or something like, I think?
Yeah, I think it's reverse osmosis.
Reverse osmosis. Yeah, I've seen people do that. Like if you have nanochannels, so have the right functional groups like that repel the ions but let the water through, then I think this is something something that is actively followed. I think even here in TU Dresden from another group.
Maybe also like just in cleaning gray water or just water from usage from homes. It needs to be cleaned. Can those membranes be used there as well?
Yeah, I think so. I mean, there's also a lot of research, for example, on oil spillage cleanup and capturing toxic molecules, be it heavy metals, for example, from wastewater, or I mean, pharmaceuticals that you can find in wastewater. If you adjust your pore size or the functional groups, you can do some molecular sieving, and this is a very, very big research field.
As you know, I'm a plant ecophysiologist. I love plants, and it grows, and I love how they work. What is your driver for your research? Because for me, it's an alien topic. It's like I got some insights from you, but what is your drive? Why do you find it so interesting?
I like symmetry, so I like looking at regular structures, and so my challenge, or what drives me, is to synthesize the structures that no one has tried yet and no one else can make yet. This is right now my biggest driving force. So just
you look a bit like an artist that is creating some new chemical structure in 2D that no one has created before.
Yeah, or like kind of like a molecular architect, like to choose the building blocks to build the framework, thinking, okay, if I put in building block A and B, how will they work together? What kind of structure will it form? And then ultimately, if we can make it, what will it be useful for? I mean, sometimes we also think, okay, this is a moiety that has been used in a different field for application ABC. And then we think, okay, can we get it into the structure as a building motive, and can it then be used by some collaboration partners?
I will completely have to change my introduction now. It's like we have a chemical artist. That's not really a possibility.
Yeah, it's a bit overselling it, but yeah. I'm at the end of the day, I'm a synthetic chemist who likes to do chemical reactions and see if we can use them to build 2D or 3D structures are also interesting. But yeah, in the field of covalent organic frameworks, actually, the 3D structures are a bit more difficult to make because you mostly use highly symmetric planar building blocks, but it's also something that a lot of people are looking into.
So you might be working towards 3D in the future.
Well, the Boron-Sulfur structure I talked about earlier is actually a 3D structure.
Okay.
We didn't plan to make it a 3D structure. It turned out, and hopefully we can submit it this year and show it to people. Yeah.
I'm sure you will. You already have a lot of really high impact papers, so you'll be able to manage that. Now, those, actually, like you said, you like the symmetry in 2D. Is that something that you have always liked? Like as a kid, were you drawn to symmetry and were you drawn to science and stuff like that? Or is it something that came later on?
It's a good question. I think that came later on because in high school, I really liked the chemistry class. I had a really good teacher, and actually, there was one of the inspirations why I studied chemistry was a good high school teacher. She was also very supportive, and then it was also, on the other hand, was my best subject in school, so that was a kind of easy pick.
It might also be your best subject because you had a good teacher.
Yeah, I think so. Yeah, I mean, this is important. That's right. And then I was a rather mediocre student in the other things, I would say. So this was kind of like a no-brainer. So I was first thinking of like just becoming like a lab scientist, not going to university. But my parents said, please go to university, and then. I mean, I grew up very close to the university, actually, where I did my PhD. I think in Belgium is maybe very similar that you don't, I mean, Belgium is not such a large country as Germany, but many people, they stay for their undergrad and grad school quite close to home. So I started studying in Bochum University, so on the west side of Germany at the Ruhr University, Bochum. Did my undergrad there. I first was working there in industrial chemistry, actually.
That's a big shift, no?
Yeah, it's quite a big shift. So I was working on titanium nanoparticles decorated with gold as CO reduction catalyst. That was my bachelor thesis. But
that sounds like a really fancy topic. You would convince a lot of people. That's interesting.
Yeah, I mean, CO reduction is, I mean, you're turning CO into CO2. So these transformations are important for different things.
You're actually creating CO2.
Yeah, I mean, CO is very toxic for humans, right?
Yeah,
you have to consider that. And if you want to get rid of it, you need some very active catalysts. CO2 is not so toxic. I mean, of course, it's not oxygen, but yeah.
Yeah, we have too much of it, but we breathe out CO2, so it cannot be that bad.
Yeah, and CO is so toxic because it binds to the iron in the hemoglobin, and then it blocks the oxygen sites, and it can also block catalyst sites in industry. So you probably want to get rid of that as well by turning it over to CO2. I enjoyed working there, but actually I wanted to go to organic chemistry in my master's. And when I started my master's, I did an Erasmus project. Also something I can recommend to everybody. Do an Erasmus year during your studies. Get out of your comfort zone, go to another country. In Europe, it's very easy. You have the Erasmus. In my case, in the chemistry department, barely anyone wanted to do it. So I could choose between different places even. And I was in Cardiff in Wales, in the United Kingdom, for 6 months. And there I wanted to do organic chemistry, but the places were already taken. So I went to the coordination chemistry lab and did ligand synthesis, small organic molecules to coordinate to metal centers. And then when I returned to my home university afterwards, I wanted to continue on that. And there somehow I ended up in the framework chemistries. There I got kind of hooked on this network building idea.
Okay, yeah, so that's really something that grew while you were studying.
Yeah, exactly. I think also it's always important to look left and right. What are other people doing? What interests you the most? Also, don't go necessarily there where you have the best job opportunities, because if it doesn't interest you and you then follow a research field, work in a research field where you get a sure job, but you don't like it, then I mean, how high are the chances you will not like the job you are working on in the end? So do something that interests you, then you will also find a job, I think, in chemistry.
Feels almost like Deco message already.
Yeah, kind of.
We're a bit early, but yeah. I also want to emphasize something that I've heard a few times, and I think that's really important, like you said as well. a teacher can make so much difference. If you have a good teacher in a certain subject, that can actually change your career path for life. So that's such a big influence. So shout out to the teachers.
Yeah, teachers and also mentors. If you have a good PhD mentor who is supportive, and also I had a very good postdoctoral mentor in the US, and also now in my habilitation, I have a very good mentor. So I've had great mentors all the way. This is really, really helpful. Also, because you are doing this, most of the things you are doing the first time then. Nobody does like 5 PhDs. You cannot know everything, of course. Also very important to have friends in your research group or at the university, because I mean, no matter what you do in science, you don't know really if it will work or not. I mean, that's why you're doing it. So I think it's always good also to discuss negative results. Chances are someone in your lab might know why something isn't working the way it is described in the literature or in some notes or something.
Based on your current trajectory, I assume you want to stay in academia. But what is it that you like so much about academia?
I like being free and doing whatever I like. So I mean, I set my research topic myself. Of course, there are certain boundaries. It needs to yield results because I have to do a report at some point. I like to read papers and see what other groups are doing. There's a lot of great research going on and getting inspired from that. Going to conferences. There's a lot of great other scientists I like meeting on a regular basis. Teaching is also something I do quite a lot, so I enjoy that as well. It's a lot of components, and I'm not sure if I would necessarily do quite well in a company environment. In the university, you are making something that is making knowledge and that is educating people. And for educating people, you can use any kind of chemistry you want.
Imagine you were not a scientist. Do you know what you would be?
I like cooking and baking, so maybe I would bake cakes or something. Maybe just a normal office job could also be interesting. Then you can focus more on your free time and your private life.
But then you would have the rigid structure that you don't like that much.
Yeah, exactly. Yeah, that's a problem. Then I cannot work on my computer until 1 in the night and come late to work in the next day.
Yeah, that's true. You have a huge flexibility, right? If you're in the drive, then you just keep working and then
Yeah,
you just
exactly.
start
Yeah.
late the next day. It doesn't matter as long as your work is done.
Yeah, exactly. That's the thing. Also, of course, it's a big topic, like psychological health of people that are like burning out, working too much. Particularly at universities, it's a big issue because if you're not in a professorship, you don't have a safe job, so to say. Yeah, and this can be a burden for many people, and then they don't watch out for themselves and prioritize the work over the mental and bodily health. So I'm pretty happy that for us, barely no one comes in on the weekend, which is good. You need to rest also. So to shut down for a bit.
Some people also have like these small signatures in their emails, which I like, and they're just saying like, I don't expect you to answer in weekends or on holidays.
Of course.
But I think that's really nice because it's also like communicating to someone else, like it's fine if you don't reply in your weekends. And I think that's important because even if you want to work in your weekends, that's fine, but don't expect someone else to do that. And I think it's really nice that some people just add that small, maybe I should add that myself. Before we close, do you have a take-home message for our listeners?
What do you say? Hit the subscribe button, hit the notification bell, follow Jeroen's podcast. We need more science in Spotify, more science in YouTube. Look into the episode of Ruben van der Vijver, who is a common friend. He was my postdoc friend, even though we are from very different fields. We met in California, and I think also, one of the things why I like science so much is I met a lot of great people through it. You work with a lot of people that have the same energy as you, and you create something new. And teamwork, very important, particularly in these days where studies are becoming more and more complex. You cannot do everything by yourself. Make friends, find friends that are complementary to your interests, and do something fun together in the lab, and push the boundaries of science.
Yeah, it's always nicer, and also it gives better results when you do something with friends.
Yeah, exactly.
This was the 18th episode of Apple Finch Pudding. I want to thank Andreas Schneemann for the information. Let's meet again for the next episode of Apple Finch Pudding.